Hello everyone, my name is Dima. You're watching the Science Rock channel. Today, I'm going to talk about the special theory of relativity, an amazing theory that overturned many beliefs about the world that humanity had never doubted throughout its entire history. Many people have heard about wonders like time dilation, the relativity of simultaneity, the twin paradox, and so on. But few people understand why this happens. In this video, I'll show you that all of this is simpler than it seems at first glance. And to illustrate it, I created an interactive visualizer that works in your browser. You will find the link to it and the project source code in the video description. Let's start with a space-time diagram. The horizontal axis will represent position in space in meters, and the vertical axis will represent time in seconds. In the center is a certain origin point, where I am as the observer. Let's take two cats, whom we'll start observing at the initial moment in time. One of them is sleeping, so he's stationary relative to us, and his world line is simply a vertical straight line. The other cat starts running to the right at a certain speed. The angle of the blue line slope is determined by the cat's speed. You can see that the angle is 45 degrees, which means he's running at a speed of 1 meter per second. Everyone knows that motion is relative. The running cat moves relative to us just as we move relative to him. There is no kind of absolute motion that is better than others. This is called Galileo's principle of relativity. It's already 400 years old. Let's try to catch up with the running cat and see what this diagram looks like in its frame of reference. To do this, we just need to shift the points of the diagram to the left along the horizontal lines, so that the running cat becomes stationary for us. The distance between the cats at each moment in time must remain unchanged during this process. So far, everything is fine. Nothing strange is happening. This kind of transformation is called the Galilean transformation. It's clear, logical, and people use it for many hundreds of years, without a second thought. But then, at the end of the 19th century, some terrible news appeared. Experiments showed that the speed of light is the same in all frames of reference. No matter how the observer moves relative to the light source, or the source relative to the observer, the measured speed of light is always the same and equals this many meters per second. That is, the speed of cats, the speed of sound, the speed of anything depends on the frame of reference. But the speed of light does not. It's hard to accept such information because it contradicts basic intuition and all the physics known at that time. Many scientists tried to find a mistake, but it was all in vain. There was nothing left to do but throw everything out and reinvent physics from scratch. A kind of physics where the speed of light remains constant and yet other physical laws don't break. How can this be done? Well, let's open a space-time diagram and try to come up with something. To start, let's draw a cat running at the speed of light. But this speed is so great that the cat's line will be almost horizontal. So, let's compress the diagram horizontally by 300 million times. This way, the lines of the horizontal grid will now mark not meters, but light seconds. At this scale, the line of a cat running at the speed of light will be at a 45-degree angle, that is 1 light second per second. Just in case, I drew another cat, also running at the speed of light, but in the opposite direction. If we start moving relative to the stationary sleeping cat, the lines of the light speed cats will change their angle, which doesn't suit us, since it contradicts the experiment. So now our task is to do the impossible, to modify the Galilean transformation so that three conditions are met. First, this is the very reason we started all of this. The lines of the light speed cats must not change the angle of their inclination. This would mean that the measured speed of light does not depend on how fast we are moving relative to the source of that light. Secondly, the new transformation must be compatible with the old one at ordinary speeds, so that we preserve at least some physics and in general common sense. And ideally, the straight lines on the diagram should remain straight. For example, the line of a cat running at a constant speed must be straight in any frame of reference. Otherwise, the law of conservation of energy would be violated. And then Einstein and his friends come along and say, "We've come up with something, but we'll have to sacrifice the Euclidean nature of our spacetime." To understand what they came up with, we need to say a few words about Euclidean space. In any space, you can place 2 points, whether it's the familiar spatial space with xyz axis, or spacetime as on our diagram, or any other kind. And between these 2 points you can measure the distance. To measure distance, we are used to using the Pythagorean theorem. On a two-dimensional plane, it looks like this. The square of the length of the green segment is equal to the sum of the squares of the length of its projections onto the axes. The formula that measures the distance between 2 points by their coordinates is called a metric. A space with such a metric is called Euclidean. In other non-Euclidean spaces, the metrics are different. It is important that the distance between points does not change under translations and rotations of the coordinate system. No matter how we move or rotate our pair of x's relative to the pair of points, the distance calculated by this formula between them will remain the same. On our Euclidean spacetime diagram, the distance between points will be like this. So what exactly did Einstein and his colleagues come up with? They said, let's replace the plus with a minus in the metric, and instead of shifting, let's rotate the points around the origin. Well, let's see. We change the plus to a minus in the metric and get this formula. A new metric means a new space. The space with this metric was called Minkowski space. Alright, that's done. Now we need to rotate. But what does that even mean? When rotating, the distance from the point to the center remains unchanged. But here, we're being asked to rotate in a space where this very distance is calculated with a minus sign instead of a plus. If, during normal rotation, points move along circles, then along what paths will they move now? These new paths should represent lines of equal distance from the center. For clarity, let's draw these trajectories with dashed lines, where the distance to the center equals whole numbers, just like before when we drew horizontal lines marking the seconds. Now let's see how they will look on the diagram. Strange. It all seems to look just like it did originally. Something's not right here. Let's try once again to compress the diagram horizontally so that the grid marks out light seconds, and we can see the light cats. It turns out that the horizontal dashed lines, along which the cats used to move, have become curved when the observer's speed changes. But we only noticed this when we zoomed out enough for the graph to include very high speeds. By the way, these new curved lines are called hyperbolas. Now let's try rotating. In regular Euclidean space, to rotate a point around the origin, you have to multiply its coordinates by various sines and cosines of the angle, but in Minkowski space, it's a bit simpler. Here, instead of an angle, it's the observer's speed. This is called a Lorentz transformation. By the way, these formulas show that if you substitute a low observer speed or an infinite speed of light, the denominators become 1, and the formulas turn into the usual Galilean transformations. Let's see how the cats will shift now as the observer's speed changes. Notice that the cats located on the lines corresponding to the speed of light remain on these lines at any observer speed. This means that no matter how fast the observer moves, the light cats still run away from him at the speed of light. It looks like we've achieved what we wanted. At any observer speed, the cats on the light lines stay on them. And at a scale of low speeds, everything works just as it did before. All that's left is to check compliance with the third requirement, that straight lines remain straight. To do this, let's place 5 cats at different coordinates, and see what happens if we start moving past them at tremendous speed. Pay attention to the positions of the cats. They shift along hyperbolas, but the lines connecting them always remain straight. Excellent, everything works. We've invented a world where the constancy of the speed of light doesn't seem like nonsense. But this led to catastrophic consequences that changed everything. Well, let's sum up. Previously, when the observer's speed changed, the points of the stationary cat shifted along horizontal lines corresponding to the same time. But now these lines have become curves. So now the points shift not only horizontally but also vertically. And vertically is where we measure time. And this is where the real fun begins. To illustrate the effect of time dilation, let's give our cats some clocks and look at the diagrams. We are stationary relative to the sleeping cat, so for us, the hyperbolas and straight lines are at the same height. His clock ticks normally, while the running cat crosses the hyperbolas less frequently than he crosses the horizontal straight lines. So, when our clock has ticked 6 seconds, the running cat's clock has ticked less than 5. As a result, for us, the running cat's time moves more slowly, but he doesn't notice it himself. The difference in time becomes greater the higher his speed, as illustrated by the red segment in the triangle. The same thing happens symmetrically in the running cat's frame of reference. If we catch up with him and look at the sleeping cat, we see that now the sleeping cat's time is slowed down. So the sleeping cat thinks that time is slower for the running cat, while the running cat thinks it's slower for the sleeping one. It turns out that time is now relative. Let's illustrate this with the example of two spaceships, each equipped with identical periodically flashing lights. As soon as one of them starts moving, the other sees that the light on the first ship starts flashing less frequently, and its color turns red. After all, the slowing of time also causes a decrease in the frequency of the emitted light. But if we move together with it, we'll see that, on the contrary, the light on the stationary ship flashes less often, and appears redder. Some people say that physicists are just putting obstacles in their own way. They've come up with some complicated model of space, and then they're surprised when oddities arise. But in reality, this won't affect anything. To check whether this is real or just a mathematical trick, let's ask the running cat to run a bit at 2/3 the speed of light. Then turn around and come back. What will we see? While we slept for 11.5 seconds, the second cat ran, came back, and only 8 seconds passed for him. Yes, this is the famous twin paradox. And the faster and longer the second cat runs, the less he will have aged when he returns. By the way, this effect was directly tested in an experiment in 1971 by Hafele and Keating. In simple terms, the experiment went like this. They took a pair of ultra-precise atomic clocks, synchronized them with each other, left one on the ground, and took the other on a round-the-world trip by airplane. After that, they met again at the starting point. The airplane flies fast enough that the relative slowing of time can be measured. And in the end, the clock that traveled on the airplane showed less elapsed time, just as the theory of relativity predicted. But let's get back to the twins and the essence of the paradox. Why is it that the running cat ended up younger, and not the sleeping one? After all, it seems like you could switch to the frame of reference of the running cat and see a symmetrical picture. In reality, however, the situation is not symmetrical, because it was the running cat who changed direction. Let's break down its journey into segments with constant speed, and look at the situation from the running cat's frame of reference. And to make sure there's no trickery involved, note that when transforming coordinates, the cats move strictly along a hyperbola. First, let's send the cat running to the right, and switch to its frame of reference. Now, let's jump 4 seconds ahead, and shift the graph downward so that the second stage starts from 0. And now, let's switch to the frame of reference of the point where the cat turns around. Now from there we send the cat back in the opposite direction for 4 seconds. Everything matches up, no trickery involved. The sleeping cat has aged more, and the faster the running cat moves, the further into the future it will be upon its return. So if you're waiting for a new season of a television show, or the release of the Nintendo Wii, you know what to do. Let's return to our cat shelter. Let's suppose all the cats wake up at the same moment, at time 0. If you observe this while staying still, everything is fine. But as soon as we start moving, say, to the right at half the speed of light, it turns out that the cats on the left haven't woken up yet, while those on the right have already been awake for a long time. Simultaneity, turns out, is also relative. If we move to the right, then on the left we see the past farther away, the earlier it isn't on the right, we see the future. It turns out that space and time literally partially swap places. And this is without even touching on general relativity yet. Wherever you look, everything everywhere becomes relative. Maybe at least distances will remain absolute. Let's take a very long arrow, lay it out in front of us, and hang clocks on both ends. Now let's measure its length while it's at rest. Exactly 4 grid nodes fit along the arrow, so its length is 4 light seconds. Now let's launch this arrow to the right at half the speed of light. Let's measure its length again. This time, the length is already significantly shorter. But why? Pay attention to the clock readings. The clock on the right end shows 2 seconds less than the one on the left. That is, the right end of the arrow is in the past relative to the left. It turns out the left end of the arrow is literally ahead of the right. Because of this, the entire arrow becomes shorter. But again, this is only the case for a stationary observer. If we were moving along with the arrow, its length would be normal. So length also turned out to be relative. By the way, this isn't just a mathematical trick, it's a completely measurable reality. Let's take 2 wires, place them parallel to each other, and run a current through them in the same direction. The wires will start to attract each other. Previously, this was explained by the fact that moving electrons in the wire create magnetic fields, which interact and generate the ampere force, attracting the wires to each other, or repelling them if the currents flow in opposite directions. But with the theory of relativity, it turned out that you don't need any magnetic fields, ampere forces, or any of that. It's enough to know only that charges of the same sign repel each other, and charges of opposite signs attract each other. That's all. Let's take a look. As soon as the electrons start moving, the distances between them contract for a stationary observer. The electrons themselves also get squashed, but that doesn't matter. Because of this, their number per unit length of the wire increases, and the positively charged copper atoms in one wire start to be attracted more strongly to the electrons in the other wire. But the repulsion between the electrons in different wires doesn't increase, because for them the electron density in the other wire hasn't changed. The exact opposite will happen if we catch up with the electrons, and look at the copper atoms moving downward. The electrons think that it's the density of the positively charged copper ions that has increased, and the result is the same: the wires attract each other. But if we reverse the direction of the current in one of the wires, the electrons will start moving relative to each other at twice the speed, and the electrons in one wire will see a huge density of electrons in the other, and will repel each other much more strongly than they are attracted to the positive ions. As a result, the wires will end up repelling each other, and the equations that describe these processes turn out to be exactly the same as before, when we use magnetic fields. Only now, there's no need for any magnetic fields. It's simply that the electric field behaves this way for a moving observer. These arguments can be generalized to any system with moving charges, completely eliminating the need for such an entity as the magnetic field. And these contractions of length open up the possibility for us to travel vast distances in as short a time as we like. Suppose there is some alien galaxy located 7 light years away from us, and we want to get there quickly. In reality, it would more likely be 7 million light years, but for simplicity, let's just say 7. According to normal logic, if we traveled there at half the speed of light, we would reach it in 14 years. And that's exactly how it would be for an observer at rest, relative to the galaxy, that is, for the sleeping cat. But what would we experience? The higher the speed, the closer the galaxy becomes. After all, length contracts. Pay attention to the blue segment. Its length corresponds to the time after which the coordinates of the galaxy in our frame of reference become 0, which means we've reached it. The higher the speed, the shorter the segment. And as we approach the speed of light, its length approaches 0. The diagram now shows a situation where we are flying at 96% of the speed of light. In this case, the length of the blue segment is 2 units. That is, we will cover 7 light years in just 2 years. And if we accelerate even more, we could reach it in as little as 1 second of our local time. But there's one catch. We could reach a galaxy a million light years away in just 1 second of our own time, but on that galaxy itself, a million years would pass. After all, for an outside observer, we would be traveling for a million years at almost the speed of light. This effect explains why short-lived particles from space, such as muons, which decay just a few microseconds after being created, can travel vast distances to detectors on the Earth's surface without decaying along the way. So, let's sum up. Since the time of Galileo, everything in the world of science was clear and well understood, until the 19th century, when it turned out that the measured speed of light does not depend on the speed of the observer. In other words, Galilean transformations simply do not apply to light. To solve this problem, it was proposed to transform coordinates not by the usual shifts, but by rotations in Minkowski space. This new transformation explained the constancy of the speed of light and did not contradict experiments at ordinary speeds. But as a side effect in such a space, time dilation, length contraction, and other wonders appeared, which not only were experimentally confirmed, but also explained many things. To reinforce this, let's look at a real-life example. Let's take a stationary ship with 2 light bulbs and ask it to blink them and sing. Now let's take another identical ship. We'll launch it into flight, and observe all this from Earth. We immediately see several relativistic effects. First, on the moving ship, the bulbs blink less frequently due to the time dilation effect. Second, these bulbs have turned red. After all, time dilation also causes a decrease in the frequency of the emitted light. Third, the left bulb on it lights up before the right one because the left part of the ship is in the future relative to the right. And fourth, the length of the ship along the direction of motion has decreased for the very same reason the left part is catching up with the right, since it is in the future relative to the right. But in the reference frame of the moving ship, everything happens the other way around. I hope that now you truly understand the special theory of relativity. But if you still have questions, I'll be happy to answer them in the comments. To illustrate, I've created an interactive visualizer where you can move sliders, switch modes, and observe Lorentz transformations. You'll find a link to it in the description. If you enjoyed the video, please subscribe. I'll be talking about other natural phenomena as well. Goodbye everyone.